Thanks. I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. We thank you for the seafarers, I guess. Help us to endure them. Help us to have a good day today. Help us to glorify you in what we do, Lord. I just pray that we learn a lot in this time. In your name we pray, Lord Jesus. Amen. There's no seafarers here yet, is there? Not till today, not till tomorrow. I came prepared this time. See here is an X-Acto blade. Let's see here. So we're in chapter 9, or my chapter 14, I think. Was it? I forget what chapter it was in my notes. It's posted. Was it 14? 14, I think. Yeah. So today I wanted to show you more first order differential equations, how to solve them. Look at a couple applications, probably Newton's law of cooling, probably some population growth, a few other things perhaps, maybe some physics. But before I get to any applications, I just want to try to find another nice problem just to illustrate the method. I suppose before I even do that, there's something that bothered me yesterday I failed to say. So, definition. So suppose you have dy dx equals to f of x comma y. Then let's say y equals to phi is solution if d phi dx is equal to f of x comma phi of x. Now that right there is the definition of a solution, an explicit solution, all right? I mean, in this context here, that would make phi, the function phi, an explicit solution of that differential equation. All right? Personally, I feel like that definition is a little bit too limiting. My concept of solution also includes things like equations, right? Like last time we found from separation of variables that circles were solutions, right, to a given differential equation. And certainly circles are not graphs of functions. So I think that saying that a solution has to be a function is, I mean, perhaps useful for some theorems and so forth, but in terms of applications, it's very limiting. So I like my concept of solution to include implicit solutions. So I think a better way to say what a solution is a little bit more informal. So here's my usual go-to definition of a solution. A solution to a differential equation is a function or equation whose differential consequence, well, that's too snazzy, sorry, which works when you plug it into the differential equation. Now, I can ask you questions. In fact, you may have already had questions in the homework from the previous. I forget. Every so often there's a homework question like, show this or that as a solution to a differential equation, right? So here, I won't teach you how to solve these in here, but I'll show you, this is an example. So if we look at y equals to cosh x, for example, then y prime is sinh x, right? Y prime prime is, again, what? Cosh x. So you can see that y equals cosh x is a solution to what? It solves y prime prime minus y equals to 0. So, if somebody asks you, is such and such a solution to a given differential equation, all they're asking you to do is to differentiate that function, plug it in, and see if it's actually consistent with the stated dependence of the variables and its derivative.
Will that always work? Or it's like the second derivative of the function, which is, minus the original function equals 0?
Will Cosh always do that?
No, I just mean just for Cosh, that it does that. Or does it work for also works for Sinch?
Well, if I had, Sinch also is a solution to that. Very good. If you had y equals to something like Cosh 3x, then you can calculate that y prime prime is 9 Cosh 3x. So this would be a solution of y prime prime minus 9y equal to 0. And also Sinch of 3x is a solution to that. You guys are trying to make me teach you differential equations again. You have to stop that. This is not these solution techniques, which I have not. How do I know that Cosh is a solution to y prime prime minus y? Where's that coming from? Nowhere. This is from the thin blue air. I just pull it out of a hat and gave it to you. Right? This is not something we've derived, but I'm just using it to illustrate the notion of solution. Because the words "what is a solution" didn't come out of my mouth last time, not clearly enough anyway. Okay, so give me a second here. It worries me to make up examples, so I want to find one from the book. Oh, come on. Bear with me. Where does he do? I've lost track of it. His first order linear equations are in section 9.1. Very good. All right, here we go. Let's try out let's try number 18. That one looks kind of tough. Sort of. So here we have x, y prime, plus y equals to 1 plus x times e to the x. We'd like to solve this. All right? Okay, so this is not in standard form yet. All right, what's standard form? Standard form for a linear differential equation is dy dx plus p times y equals to q. So last time we showed how to solve this, right? Last time we owned this one. It could not escape us. So if we can make this come to this format, what do? Yeah, just this is dy dx. No. I need a dy dx on its lonesome here. Just what? Does anyone else hear that, or is that just in my head? Oh, okay. What? Yeah, I thought I heard whistling. Okay. So 1 over x, y. Sorry, I'm just going to do it. I'm impatient. 1 over x plus 1, e to the x. So divide by x. Now it's in standard form. Now I can use the integrating factor technique. All right, so identify that p is equal to 1 over x, right? So I can calculate the integrating factor. So that's the exponential of the integral of 1 over x times dx, which is just dx over x. Well, that ain't bad. Hey, this is the exponential of the natural log of the absolute value of x. All right? Which is just what? The absolute value of x. But I'll assume that x is greater than 0 for the sake of not being annoying. In other words, I'm going to focus my attention on the solution for positive x. I'm losing something by doing this, all right? But hopefully I'm making it easier for you to follow, right?
So is exponential, is that like e to the...
Right, yeah.
You're just writing.
Yeah, I write it that way because otherwise I'd be writing e to the integral, and this is, I don't know, just bigger font. But yeah, it's just the exponential function. All right, once we've found the integrating factor, what do we do with it? Multiply the differential equation. Multiply, this is the differential equation, right? Multiply star by x. What's that give us? Yay. Okay, so one way you can look at this is this problem was already half done for us at the start, right? We're back where we started. Very good. But I wonder if at the start you could have seen what we're about to do, which is that this is the derivative with respect to x of the integrating factor, which is x times y. Now maybe you could have seen that, and that's the point. Right? You don't have to do the steps I just did if you see from the outset, if you see from the beginning that xy prime plus y is really just the derivative with respect to x of x times y, right? You could save yourself this. Now that's equal to 1 plus x times e to the x. Now you integrate both sides, what do you get? We get xy is equal to the integral of 1 plus x times e to the x, which of course is the integral of e to the x, dx. Integral of e to the x plus the integral of x e to the x. Keep reading my dx's. Of course, this is integration by parts, but I think we've done it before. Maybe you remember it. That's x e to the x minus e to the x, isn't it? So in total, x e to the x. Plus a constant, right? Now, we can check, right? If you differentiate the answer, do you get back 1 plus x times e to the x? What happens if we differentiate x times e to the x? What do you get?
X squared dx. No, just x dx.
ddx of x e to the x is equal to dx dx e to the x plus x ddx of e to the x, which is e to the x plus x e to the x, which is 1 plus x times e to the x. Which shows you that my integration is legit. We get back to the integral, right? All right, we're trying to solve this differential equation, so let's solve for y. Y is equal to x e to the x plus a constant, all divided by x, which of course you could rewrite as e to the x plus c over x if you like. So there you go. That's the general solution to this thing for positive x. But actually, for kind of funny reasons, it also works for negative x. Because we didn't really, well, anyway, I'll shut up. But. So there you go. That's the, not the, well, I don't know what that is.
So you're saying you get the same answer from x?
Hmm?
Saying you get the exact same answer from x?
Well, if you retrace our steps, right, we didn't have to do the integrating factor, right? So this, this here isn't really necessary. I guess another way to look at this is equal to plus or minus x, right? So either you're multiplying by x on the one side or minus x where x is negative. So you can kind of drop the absolute values in this technique, actually. Sorry, I really want to talk about more mainline issues here. Stupid example. Maybe I should have just made one up. Here's one. Number 22. Here we've got y prime plus 2 over x plus 1. I think the argument could be made that you can drop the absolute value there. Oh, why? What have I done? Oh. Okay, fine. I regret my life. Why did I do this one? This looks awful. All right, I'm going to try. So, first of all, this is already in standard form. Hooray. This is p. So my integrating factor, exponential integral of 2 dx over x plus 1, right? Well, that's exponential of 2 times the natural log, the absolute value of x plus 1. But then by properties of logs, we can bring the 2 inside, and we get exponential of the natural log of the absolute value of x plus 1 quantity squared. Well, that's nice, because that means that this is the absolute value of x plus 1 squared, but that is just x plus 1 squared. Right? Because you notice plus or minus something squared is just equal to the thing squared. Ever notice that? So like absolute value, or if you want, another way you could look at this is the absolute value of u is the square root of u squared, right? So the absolute value of u squared is the square root of u squared, which is u squared. I mean, however you want to look at it. Whatever floats your boat. Did you know that's the formula for absolute value? Square root of the squared. It is. Okay, anyway, there's our integrating factor. So we go up there, we multiply. I get this name. Who says name calling isn't useful? Star. Multiply star by x plus 1 squared. And we get x plus 1 squared times dy dx plus 2 times x plus 1 y is equal to x plus 1, I'll write it out, x plus 1 squared times x plus 1, oh, I guess it's not too bad. I thought, you know what I was thinking, guys? I was thinking of something like x squared plus 1 to the 5/2 power. Like that seems to invite a trig substitution, you know? I mean, you could have a problem that ends at a trig substitution, right? It just seems like he's been kind to us. Anyway, so this is what? What's that? It's what?
Plus 1 squared y.
X plus 1 squared times y, right? Equals to what? We can simplify this too, right? It's x plus 1 to the what? Two is 4 halves, right? 4 plus 5, 9 halves, yes. And now we integrate, right? So integrating both sides gives me that x plus 1 quantity squared times y is equal to 2/11 x plus 1 to the 11 halves plus a constant. Or if you like, y is equal to 2/11 x plus 1 7 halves plus c divided by x plus 1 squared by our ever-present friend, algebra. There you go. Do you see the thought process? Number one, write the differential equation in standard form. Well, first of all, identify that it's a linear differential equation, right? I mean, my first thought is, can I do separation of variables? If I can do separation of variables, I don't need to bother with this. So if I can't do separation of variables, if it's not separable, then I go to the integrating factor technique, put it in standard form, calculate the integrating factor, multiply the equation by the integrating factor, and then if you did it right, you can do the reverse chain rule, this step, and then integrate both sides, answer after you solve for y, you got it. Is that, I think I've done enough of these. I'm gonna go on. Yeah? Questions? Well, you guys can ask questions about the homework tomorrow if you got any, okay? Or right now if you got one in particular that's bothering you. Yeah?
Did you do number 16?
In this section? Oh, that's the problem with, I should staple these. What page is that on? 449? Oh, this one. Yeah, sure. This one will be relaxing after what we've been doing. Y prime minus y equals to e to the x. Number 6, this one, right? This one? Okay. Okay, so here, it's already in standard form. Great. My p is just equal to minus 1 in this case. So the I is the exponential of the integral of minus 1 times dx. But that is just e to the minus x. So is there something particular you were confused about here, or you just thought it'd be a good one to look at?
No, I was confused about that part.
Oh.
I looked at your solution, and it just had the integral negative dx, and I was confused about like where that was coming from.
Oh. Ah.
Yeah, that explains it.
Oh, okay. So then we have, very good, e to the minus x times dy dx minus e to the minus x times y equals to e to the minus x times e to the x. But these, of course, are natural enemies. They annihilate in a flash of light, and all that's left is 1. And then on the other side, of course, you have, by reverse product rule, d dx of e to the minus x times y, integrating both sides. And so that gives us y is equal to x e to the x plus c e to the x is our solution. if I did add a constant? Fine. Right? So then what do? We go here, right? Multiply the whole equation by the integrating factor, right? So what would the difference be? I multiply by e to the minus x. You multiply by but then, at that point, you would just go, oh, it's everywhere. And then we'd be back where we started. So the point is, adding a constant in the integral and the exponential just modifies the integrating factor by a positive constant multiple. So since you're multiplying the equation, I mean, you're just going to divide it out in the next step, so we don't bother. But being that you've lost points for not adding c, not you specifically, but just generally speaking, calculus students have lost points for not putting the plus c on antiderivatives, your concern is understandable. But it doesn't change anything, yeah. It's well, anyway, yeah. All right, so let's see here. So I want to talk about applications for the rest of the time, all right? So, of course, we'll still be solving differential equations, but like one of the fundamental ones is population growth, right? If the rate of the population growth is proportional to the population, this is so-called, what, exponential growth? Now, why is it called exponential growth? I mean, because the solution's exponential, right? But now we can derive that. See, dp over p equals to k dt. Separate variables, integrate. And we can integrate from, say, well, okay, so natural log, the absolute value of p. Did I do this the other day? I don't think I did. Okay. And then through the same song and dance as usual, the absolute value of p is equal to e to the kt plus c, but that gives me p of t is plus or minus e to the c, e to the kt. So let's just say p of t is equal to, let me just call this constant p naught, e to the kt. That's a pretty good label for it, right? Because if you plug in times 0, what do you get? Right, if you plug in times 0, the exponential goes to 1. So labeling that constant p naught for initial population, well, that's a pretty decent label for that constant, right? So there you go. Exponential growth. Now, this, of course, has various applications. You know, bacteria in a petri dish or whatever. Poodles on a isolated island, or rabbits. People, at some extent. But it fails for various reasons as time goes on, right? It's really only good in certain contexts. Now, the same mathematics comes up in the study of radioactive decay. If you have, which I think is not unlike like bologna in a refrigerator, right? Like if you have bologna in a refrigerator, it's bologna to start with, right? But after a few months, it's no longer bologna. So it decays, you know? And like a given slice of bologna, well, I mean, you have to think about bologna particles, I guess, but, or something like that, I don't know. They you know, there's some sort of statistical putrefaction that's happening, right? And the more, you know, the more bad bologna particles you have there, the more bologna you have. I mean, other way around. Anyway, it's the same kind of thing. So, but radioactive decay is much the same. If you have a if you have a lump of particles that are not stable, for example, neutrons. You guys know neutrons and protons make up the atom, the nucleus of an atom, right? But if you stick a neutron out on its lonesome, so-called free neutron, just sit it out there, sit it in space somewhere, just put it here, think. There is, if you have two of them, statistically one of them is going to be gone in 11 minutes. It will change into a proton and an electron and something else. So the half-life of a free neutron is 11 minutes. But that's rather dramatic. Most, I think 11 minutes, maybe 11 seconds. It's been a while since I thought about this. It's pretty long. Typical other things have, decay, much faster decay rates. So, like uranium or something, if you have one type of uranium and you leave it sitting there for a while, it will change to different types because there are these things something called weak physics that causes radioactive decay. So anyway, but the same basic mathematics goes on there. The number of particles present determines how many are changing form. So there's radioactive decay, same math. Now, if you change this a bit, you could look at something like this: dp dt equals to k kp. All right, fine. But what's the next step down this path? You could do something like 1 minus, I think p over c is the way it goes. Right. So if you look at this formula, well, how's this work? Well, if the population, let's think about this. If p is much less than c, then we have dp dt is what? Just kp, right? So what's that? That's just basically, it's exponential growth, right? But what happens if p is approximately equal to c? Yeah, here's 0? Right. So the growth rate, 0 growth, right? Let's see here. More specifically, what happens if p is larger than c? If p is larger than c, that fraction is larger than 1. The growth rate is negative, right? If p is less than c, then the growth rate is positive, right? So this is called logistic growth. This is logistic. I think this is the logistic equation, technically, but this has carrying capacity. The idea is that once the population gets to C, that's like the maximum stable population that it can hold, right? So this equation models that. Now you can solve it. I'm not going to go through it because I want to do other things, but look at this. Look at this. Look at this beast. Do you see what that is? What's that? Let me repackage it just a little bit for you. This is dp over, well, it's c over p times c minus p. To do this integral, what do you need to do? What technique? No. Oh, fine, I'll do it. So C over, you guys, you switch, look what you brought me to. Let's see your P. C minus P. A over P plus B over C minus P. What am I using? Partial fractions, right? This is a rational function in P. So partial fractions will do it. So I've got C is equal to A times C minus P plus B times P. You put P equals to 0, or you put P equals to C. That will give us super nice equations. Like P equal to 0 gives me C is equal to A times C. Well, that's very boring. A is apparently equal to 1. All right. I mean, I'll take it. A is 1. P equals to C gives me C is equal to BC. So, really? This is really not very exciting. Therefore, B is equal to 1. Okay. So apparently, the integral of C dP over P times C minus P is equal to the integral of 1 over P plus 1 over C minus P dP. Right. Now, if you'll allow me this small manga-style calculation, I would point out that this is easy to integrate, right? This is going to be KT plus C, right? Oh, I can't use C here. KT plus C tilde. There. I don't want to confuse with the carrying capacity. Okay, so what we got? We got the log of the absolute value P minus the log of the absolute value of C minus P. But U substitution says I got to put, oh, I did that. So the minus is because U is C minus P in the substitution, right? So du is minus dP. So like the integral of dP over C minus P is equal to the integral of minus du over U. So that's why I have a minus there, because it's C minus P. But then I can combine those, and you see I've got the log of the quotient of P by C minus P. And then you can solve this for P, all right? It's in my notes. I'd rather not do it right now. Oh, it's in the homework?
I don't know what you said. Oh, we got it. Oh, never mind.
I probably didn't put it in the homework. All right. So there's population growth, a slightly less simple model of population growth, right? What's other examples of differential equations? How about physics? Right? So you know the net force, right, is equal to ma, right? But what's ma? That's m dv dt, right? So we can look at examples. For example, the acceleration is minus g when v is equal to, let's say, dy dt, right? So you know the usual song and dance here. You've got a ball, right, and it's got acceleration of minus g from gravity, right? I mean, fine, here's Newton's law. ma is equal to minus mg. You divide by m, that gives you this equation, right? Okay, so now this is kind of boring what I'm doing at the moment. Let me just get here. So we got dv dt equals minus g. So we can separate variables. You're like, okay, integrate. And this tells me that if I integrate from v naught to vf and t naught to tf, well, I get the equation vf minus v naught minus g times tf minus t naught. Or in other words, vf equals v naught minus g times tf minus t naught. There you go. That's one of the I mean, you don't need differential equations for this, right? We hopefully showed you this in Calculus 1. Let me show you what we need. But what if you don't want this? What if you want to find the velocity as a function of y? Then how do you do this? I mean, I think you guys could have done this before I showed you any of this differential equation stuff. So follow this up. Let's find v as function of y. All right. So same acceleration, all right? So we have a is equal to minus g, right? Now here we have to do a little trick. So a is equal to what? A is equal to dv dt, right? But if we rewrite v as a function of y, we can use a chain rule here. A little bit sneaky. We can write this as dy dt times dv dy. Now there's a slight abuse of notation here because technically the v that I just wrote is a function of y, whereas the v I originally wrote was just a function of t. But anyway, it's a common abuse of notation. So this is basically just by the chain rule. And this, of course, is what? Well, this is v dv dy, which gives me joy to say. So v dv dy is the acceleration in terms of the derivative of the velocity with respect to the position y, and that's equal to minus g. Now that is something that separation of variables was kind of made to order for, right? So here we go. Now here's a differential equation. We know how to solve those. What are we going to do? Nah, you're thinking too hard. First thing we try is separation of variables. Can we separate variables here? We got v dv equals to minus g dy. And then integrate from v naught to vf. And on the other side, I integrate from y naught to yf. I mean, why not, right? Sorry, it's awful. 1/2 vf squared minus v naught squared is equal to minus g times yf minus y naught. Or if you like, vf squared equals to v naught squared minus 2g yf minus y naught. You may recognize this as the so-called timeless equation from kinematics. Or you might not, but you will soon because you'll take Physics 231, and then this will become familiar to you. Or you'll take Physics 231 again, and then it will become familiar to you. But something like this. But hopefully just once. I mean, we're all for recycling, but not that kind of recycling. Oh. Let's see here. Let's stick with physics for the moment. I mean, what do you guys want me to do? I mean, I can either go Newton's law of cooling for the remainder of class, or I can show you velocity-dependent friction. Let me do that one. Suppose you have a particle, right? And of course you got the force of gravity downward, right? But suppose you also have a friction force which is dependent on the velocity by, say, minus, well, let's say b times the velocity, right? So Newton's second law would give you that ma is equal to, and let's see here, we can either take downward or upward as positive. What do you guys want to do? Let's take downward as positive. It's kind of a little more natural in this case. So that would put a plus mg in that case, taking down as positive. I think this is a sort of close cousin to problem 26 in 9.2. Dr. Skambordis was singing the virtues of problem 24. Problem 24 is the same thing except with v squared instead of v. About a parachutist. So, but we'll stick with v here. So minus bv. Okay, so this is a little bit more exciting. Now we've got m dv dt equals mg minus bv. Well, that's an honest-to-goodness differential equation between the velocity and the time, right? It looks linear to me. So if I divide by m, I get dv dt plus b over m times v equals to g. By algebra. So what I did was I divided the whole thing by m, and then I added the v term to the other side, right? Or anyway, algebra. So now this is integrating factor technique, right? This is linear. I can't set separation of variables. I don't advise. So we let I equal to the exponential of the integral of b over m. Now we've been doing x in the integral. That was because x was the independent variable, right? In this problem, t is the independent variable. So I put a dt here, right? And so that's e to the bt over m. So I get e to the bt over m dv dt plus b over m e to the bt over m v is equal to g e to the bt over m. Yep.
Sorry to jump back a little bit. But
That's fine.
Yeah. You just underline, why is the v not divided by m?
Why is the v, why is the,
Oh, is b a constant and v a variable? Is that why?
Yeah.
Side? So b over m is a constant,
yes,
and v is a variable.
right.
Okay. I'm sorry. Yeah.
Still divided by.
Yeah, I get
Yeah,
it.
we're assuming that, I should
You
say,
called it out. Yeah.
we're assuming that b is a positive constant.
Okay.
That is a good question, yeah. Yeah, if b was a function, well then, we'd need longer. Or I'd be stuck. Now, thankfully this worked though. See, that's ddt of the integrating factor times the velocity this time. Now we integrate both sides. Integrating gives me e to the bt over m times the velocity equals to. This we can integrate. This is gm over b e to the bt over m plus some constant. And so I get the velocity as a function of time is equal to gm over, I'm going to write that differently. I'm going to write that mg over b plus c e to the minus bt over m. There you go. So that's the velocity as a function of time. Now that's a problem we couldn't have solved without our, the things we've just developed in the last day or two about how to solve differential equations, right? This is a problem we could not have solved before, right? Because you didn't know how to solve this kind of differential equation before we hit Tuesday, right? Well, unless, I don't know what happens in high schools in other countries. I have really no idea. But let's analyze this solution. What happens as time goes to infinity? I mean, as time goes to infinity over here, it's not very fun to think about. As time goes to infinity over here, the velocity gets larger and larger and larger and larger and larger and more negative, right? It's like if the marker just kept falling and falling and falling and falling, and there was no friction, air friction, right? It would just speed up on and on. Of course, this is really only legitimate over a very small distance anyway. This is an approximation. mg is an approximation. We'll talk more about that later this semester. But as t goes to infinity here, what do you have? How about this piece? That's e to a negative number times t, right? That's like going to like e to the minus infinity. That's like that's getting very, very small. This term is dying. So that's going to 0. This is a constant, so we just get mg over b. This is what's known as the terminal velocity. You could calculate the terminal velocity in this way, right, by actually finding the velocity as a function of time and then taking the limit as t goes to infinity. Although maybe you guys haven't studied limits at infinity. Have you? Sort of, who has studied limits at infinity in Calculus 1? Most of you. Who has never seen limits as like limit as x goes to infinity? Oh, that's good. That's good. So we'll cover those again, mostly in terms of sequences. But can you see the significance of the terminal velocity? Where's that coming from? If you go back and look at Newton's equation over here, how do you get another way you could get the terminal velocity to be what? Just set this equal to 0, right? If the velocity settles on something eventually, like the terminal velocity is when it reaches a point where it's neither speeding up or slowing down, right? That's where the acceleration is 0. So that's where the net force is 0. And so if you set that equal to 0, well, that gives you, right, bv equals mg, so v equals mg over b. So there you go. Intuitively, it makes sense that that's what it is, right? Wow. Anyway, I guess I still haven't shown you Newton's law of cooling. And most of the time I'll try to spend tomorrow talking about orthogonal trajectories. Just to give you a preview, imagine somebody asked you, so here's a grid of curves, right? How would you find another grid of curves which meets that grid perpendicularly? So like, I can't do it. See, so like everywhere they meet little, like, right angles. So these, if you can find two families of curves which are related in this way, they're said to be orthogonal trajectories. I'll show you tomorrow how we can use differential equations to create such orthogonal grids. Thanks, guys.